So my name's Andy Wingo. I work for a company out of Spain called Igalia. We do a lot of consulting around WebKit, and as such, I've gotten into JavaScript Core a bit, and JavaScript Core is the JavaScript engine of the WebKit project itself. I've hacked a bit on VA before, on JavaScript Core, but in reality, I'm a traveler in foreign lands here, as my heart is from the Scheme language. So it's interesting coming into these implementations from the outside and seeing, what's really going on. And the tag for this talk had a bit of hubris associated with it, I think. Claiming that JavaScript Core is as fast as V8 on its own benchmark, and as we'll see, that claim has a shape to it, and some of that shape is true, and some of that shape is not quite true yet. But let's take a look at the DFG, at the optimizing compiler of the JavaScript Core engine, and see, what is it that it actually does. So as I mentioned, the DFG is JavaScript Core's optimizing compiler. The standard architecture of these JavaScript engines is you have something for dealing with cold code and something for dealing with hot code. And for JavaScript Core, we have the low-level interpreter for very cold code. There's an intermediate phase with what we call the baseline JIT, which is a JIT that doesn't do any global analysis or optimization. And then we have the DFG JIT, which is able to take a bit more time, has a bit more information, and can take a bit more of a global view on your program. So this much is fairly well known, but I don't think it's very, well understood. What it is that this engine does with your code and how it works, and what its performance characteristics are. And so I would like to take a more empirical approach to it. I would like to, measure the DFG JIT and see how it does on various representative test cases, and see when it does this. When does it kick in? What are its dynamic characteristics? Not simply performance as a number, which is great for the marketing folks, but performance as a shape and a distribution, which is much more interesting from a perspective of understanding the software. I'd also like to take a look at the assembly code that is produced by this. So I promise it won't be all assembly, but I think it's kind of interesting to see how your JavaScript is translated into what machine code when you run on a browser with JavaScript Core. So as my tool in this regard, I'm going to use the V8 benchmarks, V8 version 7 benchmarks. And these benchmarks are really geared towards optimizing compilers, right? They don't test anything else in your system. They test your optimizing, the output of your optimizing compiler, and also your garbage collector as well. And the reason you can know about these is they take quite a long time to run. And they take a long time to run because they take a full second to warm up the code for each benchmark, and then they measure over another second how they take a number of iterations until you get up to a second of iterations of these benchmarks, and they divide the time by the iterations, and you get a time per iteration. And that time ends up going on the denominator of the result, so that higher values on the V8 benchmark, as we all know, actually correspond to higher performance. And so it's very good for measuring the best that your compiler can do, but it's not so good for investigating characteristics of the implementation. I will take a look first, though, at what are these numbers. I have a graph here. I'm not sure if these numbers are terribly visible to y'all. The green bars correspond to this baseline JIT, which doesn't do any global analysis, and the yellow bars correspond to the DFG JIT, which is the optimizing compiler. And you can see we get 3 and 4 times improvements, except on the regular expression one, which I'll talk a little bit later about. Now, I want to also use this graph to introduce an idea I'm trying to work on in this presentation. It's probably not finished and can be much better, but it's that performance is not simply a number. It is a distribution that you can sample. You need to take a number of samples and see what is the range of performance that I expect. And so at the top of all these bars, I've got little histograms superimposed. I don't know if I'm doing this quite right anyway, but you can see, like, for example, on this DFG JIT histogram, we see that they're all very tightly clustered, whereas on this other DFG JIT histogram, we have a bimodal distribution. They're pretty tight, but your performance tends to cluster those two values. And that's something that you really can't capture with a median. And I'm going to use this sort of thing as we go forward to really pull apart some of these benchmarks. And really, I'm not going to use the straight V8 benchmarks as my tool. I'm going to hack them a bit to see what are the dynamic characteristics of the DFG. I'm going to make the warm-up time variable, starting from no warm-up at all the way up to a second, with more samples closer to 0, so after 0 milliseconds, after 5 milliseconds, after 10 milliseconds, meaning after 10 milliseconds, what's the performance I can expect on my web page with JavaScript Core? After 25 milliseconds, what's the kind of performance I can expect? And then the thing I measure after the warm-up is going to be 5 milliseconds of runtime. And it's a good measure of the code that the DFG can produce, but it's a very tricky measurement as well because it's sensitive. Let's say in those 5 milliseconds where I'm measuring, what if GC hits? Well, I'm going to get much worse results for that particular run, for example. Or what if the optimizer decides to optimize a lot of code in that 5 millisecond window? Well, also I can experience some slowdowns. And as well, we have some issues with timer precision in JavaScript for measuring these things. I'm using the more precise timer that's available in the JSC runtime called precise time, which gives me a bit more precision in this regard. But all of these things, these unexpected pauses, these sources of variation in performance can also affect your real code. So I think it's not unfair to actually be measuring these things. So in this experiment, more than other ones, we really need to take a look at this shape of performance again and see what's going on. With that out of the way, let's take a look at the first V8 benchmark, which is the Richards benchmark. It's a scheduler, and it uses some bit operations for maintaining the states of tasks in the scheduler. And it uses a bunch of objects with properties and prototype resolution and such. And what we can see here is that here at 0 milliseconds, we're starting off with pretty poor performance, which is natural. You don't want to spend your time optimizing code that you don't know is going to run. But after 5 milliseconds, 10 milliseconds, certainly after 75 milliseconds, we're up to our peak performance. These vertical lines indicate runs of the optimizing compiler. So you can see that they're all clustered before 75. You probably can't even read that. Let's go to 0, 5, 10, 15, 25, 40, 75, 1, 200, 320, 500, 700, 1,000 milliseconds, right? So from 0 to 1 second, this is the dynamic profile of the DFG performance. And what we see graphed here is the distribution of performance results that I've taken. So I've, for example, warmed up V8 for 0 milliseconds and then measured the next 5 milliseconds 50 times, right? And those 50 values are plotted here. Same for 5 milliseconds, same for 10. I don't know. I tried to make it understandable, but it's a novel graph kind, and that never goes over quite so well. What we see, though, is performance is fairly tightly clustered. The paint, if there's more paint, it means that there's a higher variance in the performance. And here we see things are fairly tight. It goes up, drops down a bit for some reason I don't quite understand. But then no optimizing compiler run happens after 75 milliseconds. So 75 milliseconds in this benchmark, and the DFG's done all that it sees fit to do. And so we get a 3.7 times performance increase. 1.0 would be no increase at all on this particular benchmark relative to the baseline JIT measured over a full second. And now we get into hardcore stuff. One of the things that turned out, we'll just take an example of one of the functions that we went to optimize here. I don't know, how many of you have looked at the source code for the V8 benchmarks? A few of y'all? The engine hackers, I see. All right. So for the rest of y'all, here's the JavaScript up here. We add something to a task saying, is suspended. We do a bit and compare, and we have another clause that they're logical ORed together, and we return it. And the assembly that's below is what you can see on the screen right now corresponds to this.state bitwise and with state held. First, we get this, which is a local variable, and that's just a memory reference. We check that the this has the prototype that we saw when it was initially compiled, when it was optimized. And if it does not have this prototype, we're going to jump to this bailout, at which point we de-optimize, which might be a word you've heard from other discussions of optimizing compilers like Crankshaft, for example. Then once we've verified that the this object has the shape that we're expecting, we directly reference a field in the object using what the V8 folks call hidden classes. We get the global variable corresponding to state held. It's unfortunate that we didn't inline this to a constant, but OK. And then we go ahead and do the bitwise AND. The first 4 instructions correspond to type checks that the this.state and the state held are both integers. R14, this is a 64-bit assembly code, and R14 holds the number tag. So we compare the number tag on the value. JavaScript Core uses the NaN boxing technique. NaN boxing, folks heard of it? Yeah, awesome. You guys are great. If you haven't heard of it, search NaN boxing on the web. Also search for none boxing. And I don't think there's any pugilistic encounters, but I don't know. Finally, after this, we have some comparisons. We compare the value to 0. We invert it. We actually store it to memory. That's the set local. And we do a branch. And this is suboptimal, to be honest. Like many of these things could be joined together, but these are the instructions that are produced for that very first part of this function. There's some more, and finally we return. And then after the end of the main path, all the bailouts, all the points where we jump to if something wasn't expected. I got to check myself, because I could talk about this forever. That's just the first benchmark. So second is DeltaBlue. It's a constraint solver. And we get a fine speed up on this one. We get a bit more paint here, as you can see. There's more yellow. There's more variance towards there. And I'll talk a little bit more about what that means. But on this one, it's very important to inline. But we see some, if I look at the logs, and I'll talk about how to get the logs a little bit later, I think. Yeah. We see some entries like delaying optimization for this thing. And it's called in a loop because we have insufficient profiling. And so this indicates that, for this optimizing compiler, as with all JavaScript optimizing compilers, we need what they call profiling, which is the runtime type feedback, the type information. And there's actually an option to tweak how much it weights or doesn't weight for some profiling information. And in this case, it hits the maximum of 5 attempts to profile. So it starts first after 20 milliseconds, and then eventually, after trying again 4 more times, at 40 milliseconds in, it goes ahead and creates the optimized code. It's like it would like more information, so it's going to wait for it. It waits. It doesn't find it, so it produces the code. And that's the general flavor of things. This is I looked through the logs for what kinds of functions were actually compiled in this early phase. And if I go back to the graph, sorry for switching back and forth, we see that it's really between 15 and 25 and 40 milliseconds is where we start to jump up to our level. And that's generally the time range that your optimizing compiler will kick in. And I saw this is one of the functions. It doesn't look very hot to me. I mean, I haven't actually run the dynamic profiler and seen if this is hot, but just looking at the code, it didn't look like it was going to be something that was particularly hot. And what that indicates to me is that here we just have a lot of work to do. And indeed, if we go back, I apologize again, going back, we see a lot more vertical lines in this one compared to Richard's. And they go a lot later. They go after 75. It seems there's some all the way up at 1,000, and I'm sure if it ran for more would run. So some code, especially code with small functions that needs a bunch of inlining and such, it's going to take some more work to be optimized. Richard's, the previous example, was a bit simpler for the DFG to work with. The next one is crypto. Crypto is kind of interesting. It deals a lot with integers, and it deals a lot with arrays as well. Again, we see a lot of lines. You can see some notable clustering as well. Clustering is like when a line is bigger. That's because 2 lines are drawn really close together. The DFG optimizer will kick in based on a profile count. So for example, a loop executes 1,000 times or something. And that can lead to clustering because there are a lot of loops and functions whose execution counts are linked. If you call this function 1,000 times, then this loop will run 5,000 times, and this other function will run 1,000 times. So they can all kick in at about the same time. So you can get this sort of clustering effect. It usually doesn't affect performance, I don't think, maybe it can cause an optimization slowdown, but I don't know. It's an interesting characteristic. But I like this one because crypto is a great benchmark to optimize because there's lots of, classical compiler optimizations that us compiler nerds really dig on. And this is one of the functions that's in the benchmark. As we can see, we have a lot of integer operations trying to keep in the range of integers that are efficient in JavaScript. And if I take a look at one of the particular lines, which is fetching a value from an array and then doing a bitwise AND with a constant, we can see that we get the array, which is this array. We fetch that out from memory. We get I, which for some reason is in memory as well. I don't think it's actually a good idea for it to be in memory, but OK. And we get this. This is actually a relatively new thing. Just landed about a month ago, this butterfly representation. This is a way in the future to store out-of-line data, like the elements in an array, to potentially store them as unboxed values. It's not completely taken advantage of yet, and I think that's one of the things that in JavaScript Core, in the DFG, we'll start to see in the next couple months or so. But this is a pointer to either a small amount of inline data. So if your array only has 2 elements, for example, they're probably going to be allocated in the same block as your object, or a pointer to out-of-line data containing the rest of the array. The get by val checks that the integer is in bounds for the array, and if not, it bails out. Fetches the value and checks if the value is a whole, and if not, it bails out. And then finally, we do a bitwise AND. Another thing that I wasn't mentioning before is that between these operations are the part of the internal representation of the DFG compiler. So they correspond loosely to things that you need to do semantically in JavaScript, but they don't correspond exactly to bytecode, and they don't correspond exactly to the specification either. But what we see is that, for example, we have we get this array and we put it in R10, and then down here we use R10, and then later on we can use these values directly in those registers. Register allocation is obviously a huge optimization that all of the optimizing compilers do, and so even if you don't have a lot of type information, running the optimizing compiler on a piece of code can still be quite advantageous. Right. So ray trace. Here we have an interesting example. It's the first floating point example in the V8 test suites. It uses some floating point math, and it uses objects with floating point fields, so like this.x being a floating point number. We see very tight performance here, and then as we warm up a bit more, we start to see a bit more variance. And whenever you see variance in a very small benchmark like this, it means that something is slowing down the benchmark sometimes, but not some other times. So any guesses as to what this could be in this particular case? Yes. Yes, exactly. The reason we have so much variance, and you probably can't see this right now, but it goes from here all the way to here. There's a histogram line drawn there, is because sometimes we hit garbage collection and sometimes we don't. In the ray trace example, we get a lot of short-lived objects with floating point fields. So you can get very good performance as long as you don't hit GC, and if you do hit GC, you get less performance. And I'll talk about that a bit more when we get to the more strong tests of the garbage collector later. As one example of code that the DFG works with for this one, we have this normalize function, and it takes a vector and it returns a new vector, and it normalized. As it compiles this function, when the DFG gets to this magnitude, it's going to inline the code for this magnitude, which is pretty awesome optimization. Also done by other systems, but it's pretty key to do. And I just want to focus a bit on what happens when we store the result for this.x divided by m. We ended up dividing by things that are placed in SSE registers, so it's just one instruction after we've loaded up the values. But then when we go to store it, we re-add a number tag on the value in the high bits of the value, or I think it rotates the value around, actually. And we store it as a sort of general JavaScript object, which only occupies one word, but in into this object, which means that we don't have fields that are unboxed values in JavaScript core. We don't have this.x can be like an int32, for example, or this.x can be a float, and we always know it's a float. Otherwise, we would leave off this tagging step. Early Boyer. Again, we see a lot of paint because we see a lot of short-term allocations. These are two benchmarks that were translated from Scheme, actually, by an automatic translator, by the same fellow that does the Dart to JavaScript translator, incidentally. And so what we see are a lot of calls to small functions and a lot of allocation of short-lived objects. So this is something that a generational collector will do really awesome on. But in JavaScriptCore's case, when the garbage collector needs to run, it actually stops everything. And then it scans the entire space in parallel. I mean, you have maybe 8 cores in your system or 4 cores, and it will use all of them. But it does have to scan the whole space to see what's live and what's dead, and then it lets the program go on. And that leads to this, these huge variances here, and ongoing. I think the outside color corresponds to 90% of the samples, and that red in the middle is the middle 10%. You can think of the reddest red as a kind of median line on these. So it's just an indication of this thing. If you take nothing else from this presentation, is that numbers are really awesome when you're having shootouts and races and marketing and things like that. But if you actually want to understand anything about your own performance, then you need to treat performance as a distribution of values and not simply a number. Next, we've got the regular expression benchmark, and there's not really anything to say here because the regular expressions have their own compiler in all the engines, and it's not really subject to the optimizing compiler. And so the DFG doesn't really do anything for us here. And that's basically that. It seems to run, but very few times, maybe 15 times or so, giving us a speed up in the loops around which the regular expressions run, but not in the regular expressions themselves, which take the bulk of the time. Finally, we're getting to the end here, I think. Good. We have the splay benchmark, which tests allocations that are very long-lived. So it's terrible for generational collectors. JavaScript Core actually does fairly well in this. But what you can see, again, is the huge amount of variance here. We go from all the way on the bottom here when we have to stop the world and mark an enormous heap to something that's quite good up there. And you don't see this kind of variance if you just look at the numbers in the end. Like if you just look at the raw performance numbers measured over a second, because if you measure a second, you're amortizing all these garbage collection costs. You're not measuring, what is your maximum pause time, for example. So in this case, we're seeing a pretty poor maximum pause time because of this stop the world, although it's parallel, but stop the world marker. And finally, we have the newest addition to the V8 benchmarks. I guess if they're still around and we don't all move to Octane benchmarks or such, which is a Navierstokes benchmark. It has a large array of floating point numbers, but not using the typed arrays. So what this really measures is, okay, first of all, are you doing good floating point wise? Does your optimizing compiler deal with floating point well? And can you automatically turn arrays of floating point values into arrays of unboxed floats? And in the case of V8, they can do this. In the case of JavaScript Core, we can't. So, for example, this getByVal fetches a value at the index with the same range check and is it a whole, and we get some local value, I think, and then we turn this value we got into a double, which actually doesn't take very much code, but it's more than if it was an unboxed array and we knew it was a double already. So yeah, no automatic turning of arrays into double arrays. Finally, before I close, I'd like to mention how I got this data. If you run JSC, and I think there's so many Apple laptops around here, you probably have JavaScript Core installed if you can locate the JSC program. If you run it with --options, it gives you a spit out of knobs you can turn. The -d will dump bytecode, which is useful in together with disassembly. If you say show DFG disassembly, but in order to get the timestamps, the information that I showed you, you have to enable some verbose logging. And the graphs that I showed you, I measured them without the verbose logging, and then I superimposed the DFG vertical bars after enabling verbose logging. So they were from separate runs and not entirely identical, so don't try to correlate those too precisely. Right, so back to the hubris, I guess. JavaScript Core is fast as V8 on its own benchmark and stuff. And yeah, it is. And it's faster. And it's slower also. Because, we got a bunch of different tests. Like, we're doing real great on Richards. I say, we as a JavaScript Core hacker. I don't actually have a dog in this race. But, do great on Richards, not so great on DeltaBlue. The same on crypto. Really eating it on early Boyer. But we're, picking up on Splay. And it's just, a classic example of, boy, JavaScript Core is, really killing it on Splay, right? But the pause time, it's not on this graph, right? You can't see it because those costs are amortized over the entire second of collection. So yeah, that's JavaScript Core's optimizing compiler. I'll take some questions now. Sure.
First of all, awesome talk. Loved it.
Thank you.
Being a VM geek, obviously I do. The question I have is for the butterfly. Forget what that was. Not view, but something else. Is that intended to be for arrays only? Or is there a plan for making unboxed values for objects as well, for property?
I think it's for both. I haven't talked with the fellow that implemented, but as far as I understand, it's for both.
Sounds very cool.
Hi. Are there plans to expose this information for developers? Like, when are certain parts of the code hot? When is your program actually doing something bad that's throwing off the JIT and whatever? Because that's actually something that we're missing right now. That kind of information. That's
a good question. I think the general answer to that is the profiler, and the profiler I believe is hooked up to the inspector. And if it's not, then that's a problem. I mean.
That doesn't really tell you that it's actually throwing it off. I mean, it just, you see a decrease in performance, but it doesn't really tell you, which part of the code is causing it, or why your JIT is failing, basically. So is there, I don't know, like maybe like a heat map?
That would be awesome. It's not implemented yet.
Okay.
So JavaScript Core has 3 different compilers. That seems like a fairly high number. Do they really need that many?
I don't think so. I believe the plan is, well, the plan is driven by results, right? So does it slow down something or not? And I think the low-level interpreter has seemed to work for just munching a lot of code that doesn't run very often. And the DFG works for hot code. And I think the question is this baseline JIT necessary? And it seems that right now, to remove it is not worth, it's still a performance improvement. But I think that's probably due to inefficiencies or things that aren't complete in the optimizing compiler, more than any fundamental architectural advantage. But I'm kind of talking out my ass, so.
Just to double check, as I understand, the JIT compiler runs in threads, so you have to stop the world in order to compile. So like the bunching of compilation could cause pauses in and of itself as well.
Yeah.
Okay, I guess that's it. Thank you very much, Andy.
Thank you.